We have 2 more talks, and I want to finish this on time so you guys can enjoy the rest of your day. Okay, Drew?
Great. Hi, I'm Drew Lindsley. I'm a postdoc at Brown University. I gave a talk earlier today, so if you're new, let me introduce myself. If not, sorry to repeat myself. I work with Serre there, and the talk I'm going to give you, just to anticipate, reflects a lot of the work that he did with Tommy Poggio, and so there's going to be a lot of discussion about the max pooling, building off of what John was talking about earlier, so hopefully we can come to some kind of agreement about the right kind of pooling operation used in visual cortex. But just to start us off, I want to lead up with an agenda. So I will first talk about just a basic computational unit for feedforward processing in visual cortex, and really the power of this basic construct. I'll next move on to the type of architectures that I mentioned, these hierarchical architectures, which now have their cousins in computer vision taking over the world, the cousins being convolutional neural networks, and the original progenitors from neuroscience being things like the HMax, although there's many others, which I will also mention. And finally, we'll have some fun, and I will talk about some of the inductive biases of biological vision, which I believe are missing in our current approaches to computer vision. So starting us off, at the beginning of today, I talked about early vision, and I didn't really name these things, but in early vision, we have an array of cells which perform different kinds of functions. There's retinal ganglion cells, which I'm not including here, and their activity is passed to cells in the lateral geniculate nucleus, the LGN. And these signals are then passed to early visual cortex, or V1. So LGN cells pretty much fall into 2 categories. There's the on-off, or off-on, that's on-center, off-surround, or vice versa. And one kind of cell found in visual cortex, and this is found in seminal work by Hubel and Wiesel, is called the simple cell. So first, let me show a little movie about how this stuff was found, because it's just so cool the way that these guys did this. Again, this was in the 60s. They had anesthetized cats, and they would stick an electrode into a cell in either the cortex, the LGN, or retina of these cats, and they would flash stimuli on screen, and as you can hear, the neuron would emit some kind of electrical response when certain kinds of stimuli were flashed, and this allowed them to map out the response characteristics of different cells in visual cortex. So just to jump ahead, some diagrams of how they map these cells are shown here. A and B are the on-center, off-surround cells. Off, or inhibitory regions, are denoted by X's, and on, or excitatory regions, are denoted by triangles. And so that is basically the pattern found early vision. So we're talking about retina and LGN. But once you move into visual cortex, you see some more complexity in the responses of cells. So you see these oriented regions where you have oriented on or oriented off responses. And so this generated the really paradigm-shifting hypothesis that these 2 things are related. So really that there's some kind of wiring, a connectivity pattern that passes signal from cells in the LGN up to a single cell in cortex in V1, this so-called simple cell that's combining the responses from those basic LGN cells. And you can see that here. If you imagine that, as I mentioned earlier, you have replicated computational units across the visual field. And so here, what you can see are 3 different LGN on-off, that's off-on cells at 3 different locations in the visual field. So the idea here is that a downstream cortical simple cell is taking some combination of the responses of those 3 separate LGN cells, and that's what yields the special response profile that I just showed you for simple cells. And if this is true, then what you should see is that you flash the preferred stimulus from that simple cell, and it should cause that whole ensemble of cells to respond. And then, there we go. And then as you start to vary the orientation of that stimulus, you'll see predictable decreases in responses from each of the units in the group. And a lot of work has been done to verify this relationship from LGN to V1 simple cells. So the study I'm showing you here took LGN cells, you can look in the bottom left-hand corner, LGN cells, and mapped out the receptive field. So 2 LGN cells, which responded to a stimulus, and then a V1 cell, which had an overlapping receptive field with those 2 LGN cells. And what they found is that the response properties of those cells indicated that there was a message being passed from the LGN cells to the V1 cell. And you can see this in the cross-correlogram, in which there's it's in the bottom right-hand corner, in which there's a slight delay, maybe it's a little bit difficult to see, but a slight delay in the optimal correlation between the responses from these cells. And this delay corresponds to about 5 milliseconds, which is notable because that is hypothesized to mean that there's about 1 synapse separating these LGN cells and V1 cells. So maybe, in fact, this connectivity motif is real. And moving on, Hubel and Wiesel also noticed another class of cells that had a different set of response properties. This was what they termed the complex cells. So these are really interesting because, as you can see here, they have a bit more general response profile than the kinds of cells that I showed you earlier. So as this vertically oriented bar is passing through a region of the visual field, you'll hear firing. So they're responding at all positions of that vertically oriented bar. And so again, with this old school but very, very elegant experimentation, they found that if you passed a preferred stimulus across locations, a complex cell would fire pretty much the same across those different locations. But when you reoriented the stimulus, when you changed its orientation, the complex cell would stop firing. And so this gives us the idea of a pretty simple extension to the model that I described earlier, in which you have simple cells at 3 different locations in the visual field, which project or have projections to a single complex cell. And this complex cell will then activate regardless of if a preferred stimulus is here, here, or here, regardless of a local, with some local invariance to position. Similar studies have validated this idea of feed-forward connectivity from simple to complex cells. So this is quite similar to the study that I mentioned earlier, where 2 simple cells were located, the receptive fields of 2 simple cells were located, as well as a complex cell with an overlapping receptive field. And what they found is that, again, about a 5 millisecond delay was between when the simple cells responded to their preferred stimulus versus the complex cell in the same receptive field. Again, this suggested that there was basically 1 synapse separating the simple and complex cells. All right, so now I've described a pretty elegant, I think, for biology, construction or motif for processing visual information, which begins with the retina. And retinal cells and LGN cells will have pretty similar response characteristics. But nonetheless, ganglion cells will project to LGN cells, and several LGN cells will project to a single simple cell, and several simple cells will project to a simple complex cell. But let's drill down on these final 2 stages a little bit. And I'll present this in a slightly more technical way. So imagine you have a stimulus. And imagine you have simple cells, which I'm showing you here as just oriented Gabors of different phases. So what we would expect with our complex cell model that I just laid out is that we have some complex cell C at the bottom there, which is combining or pooling responses from those 4 different simple cells. But something else I need to mention before going into and characterizing this pooling function is another bit of complexity in visual cortex, which is still a wide open question. And I will just touch on it because it's quite important for coming to some consensus about the kinds of pooling functions that can be implemented in visual cortex. So this is called normalizations. And there's a long, long history of normalization models in both visual psychology and neuroscience, going all the way back to Stephen Grossberg in the 60s, 70s, and Mingola in the 80s. But more recently popularized by David Ehinger and Matteo Carandini in the mid-90s with their divisive normalization model. And the way this model works is pretty straightforward. Given a set of K neurons, you can look at the equations on the bottom right, given a set of K neurons, the response of the ith neuron will be divisively normalized by the sum across that whole population of neurons. And so what this will do for the response of any particular neuron is implement a pretty basic form of gain control. So that's pretty cool for a wide variety of reasons, many of which I will not go into here, but most basically, you can see an example of this in figure D, panel D up there, in which the contrast of a stimulus is varied, but the overall shape of the tuning curve does not change. And so this is because the activity of the population is being changed as a function of the whole. Okay, so what this also allows you to do is, based off of the normalization that's being implemented, the type of pooling operation at the complex cell can be changed almost continuously. So most popularly, I think, at least for this whole audience, is the max pooling function, which implements something like an OR operation. So if a stimulus is present in a receptive field, regardless of where that receptive field is, the max pooling operation will say, let's accept that that stimulus is there. Of course, John presented some information, some evidence earlier that this is not always the case in cortex. And I think the answer to this question is yes, meaning that cortex can very flexibly change the kind of normalization, or sorry, kind of pooling function that it's implementing based off of the normalization that it's using. So if you imagine a softmax, basically one easy way of doing this would be to change the temperature of a softmax. And there's a lot of evidence that cortex does this. By changing the temperature, you can go from basically an average style pooling to all the way to a max style pooling. And so this is what many have thought is going on, at least in visual cortex. And as one aside, the reason why max pooling has been touted so much in visual neuroscience is because people are looking for max pooling in visual neuroscience. So I think if people were looking for other forms of pooling functions in visual cortex, they would probably find those as well. And the reason why max pooling is really nice is because it allows us to overcome this superposition problem. So imagine the stimulus, the oriented bar on the left, and imagine a complex cell that is implementing some kind of angled filter. If you have linear pooling, the response in that complex cell will be greater than the response to any of its afferent units. Versus if you have max pooling, its response will be equivalent to the max of its afferents. And so there is, as I mentioned, evidence for max pooling in visual cortex. In the study I'm showing you on the left here, they considered 3 cells. There's RA across the columns, RB across the rows, and in between those are the responses of a complex cell that shared the same receptive field. What they also show, so in gray is the complex cell response, in black is the predicted response of the addition of RA plus RB. So if some kind of linear combination of those activities was being used. And what you'll see, maybe it's difficult to see here, is that across nearly all those response profiles of the 2 cells, the linear combination overestimates how the complex cell would respond. This max pooling operation has also been extended to higher layers of visual cortex. So right now we've talked about retina, LGN, and V1. There's other layers of visual cortex. There's V2, V4, et cetera. V4 is thought to respond to mid to high level characteristics of stimuli. And so here, these researchers presented two of the patterns, one on the row, one on the column, within a receptive field of a V4 neuron at the same time. And with some visual inspection, you might be able to see that across all those combinations, there's a max-like effect across the combination of those two stimuli. All right, so thus far I've presented this complex cell model, and let me recast this a little bit more abstractly. So you have something like simple cell responses, which are oriented Gabors. Indeed, you can square the response from these simple cells to get sensitivity to both phases. You can add some kind of normalization to your complex cell model, which can help with gain control and also give it flexibility to implement different types of pooling operations potentially. But let's throw that out for now and just use a hard-coded max pool because we can think about what this max pooling operation does for us. As I mentioned, it's going to provide some tolerance to a preferred stimulus across space and potentially some scale as well. And so that's really the basics for the feed-forward building block of computation in visual cortex. And long ago, I guess that's only 23 years ago, it is long, it was thought that this could not be implemented with merely a feed-forward pass, but rather there must be some kind of recurrence or potentially top-down influence that allows for these complex cells to exhibit their interesting response properties. This was disproven. I won't go into that. Instead, I'll go into the evidence for why feedback is not responsible for these response properties. So in this study by Förster and colleagues, they used a technique in which they looked at visual cortex, V1, V2, and applied a cooling device to V2. And what that cooling device did is it suppressed activity in V2 neurons. So if there is a hierarchy from V1, V2, you would expect that V2 might feed back onto V1 to give complex cells some of these interesting properties. And by cooling V2, you would lesion that ability. And so what they found is that when you cooled V2, it didn't make a difference, and you still see this invariance to different stimulus characteristics in complex cells. So now we have the building block. Tommy Poggio's group did a lot of work on this, but I'll just talk about them right now. In another slide, I'll talk about all the others that have also thought and worked on this, or just a few of them at least. There's many. But Tommy Poggio and his group, along with my advisor, Thomas Serre, worked on a model called HMax. Okay, so this in many ways is the progenitor to, as I mentioned, to convolutional neural networks because of its replication of this basic computational building block to build up depth and higher order representation. So going from V1 to V2 to V4, all the way up to high level cortex, inferior temporal cortex, which is in primates, not in humans, but thought to respond to object parts or whole objects. And so earlier models include Hupel and Wiesel's model, the Fukushima model, and many others. And what's important to note about this line of work, this happened in parallel to the development of convolutional neural networks. The motivation of these groups, if I can characterize them, it was to fit neural data. So there was no backprop involved in these models. And as I'll talk about in a few slides, it turns out backprop eventually helps fitting neural data as well. But for now, let's just focus on the HMax, which was constrained as much as possible by biological data. So V1 contained these simple and complex like cells, oriented Gabors, followed by pooling functions and divisive normalizations. And these building blocks were repeated in such a way that the receptive field grew consistent with how recordings of receptive field sizes were in primate. And this was a really powerful model is a really powerful model for explaining high-level visual cortex activity. So this is a paper by Serre in which they recorded activity from IT cortex in primate in response to objects of different sizes and locations. And the question here was, does the HMax model exhibit the same kind of tolerance across size or scale and location as a linear decoder put on top of activity recordings from IT cortex, if that makes sense. And so in the bar graphs above, you can see that IT decoding performance and the model's performance were near each other. And this was done by training on these on a stimulus of one scale and location and testing on or various stimuli of one scale and location and testing on left out stimuli of different scales and locations. So the HMax model exhibits similar kinds of invariances as high-level primate cortex. And it also has a lot of similarity to behavioral decisions made by human observers during rapid vision. So there's this, this is a brief aside, there's this concept of rapid vision in which you, and John mentioned this a little bit earlier, in which you show a stimulus very briefly or speed responses for human observers to a stimulus. And the idea is that by doing this, by adding the time constraint, you can force as much as possible in behavioral data people to rely on feed-forward mechanisms to make their decisions. So in this experiment, responses were, or images were shown, and responses were forced to be within about 600 milliseconds. So it's a really rapid design. And people saw images of animals or non-animals, in which the animals were shown in different scales, and of course, positions and poses in the environment. As you can see on the left, the model did a good job of explaining human behavior on this task. So HMax is a very nice model for explaining the brain, at least the feed-forward passive information through the brain, but it's also missing quite a bit. This is a study by Quiroga et al. From 2005, done with Gabriel Krayman, Christoph Koch, and others. And what's really cool about this is they developed this technique in which it's not really a technique, they showed up to hospitals and patients in hospitals had incurable epilepsy. So the only approach then was to stick a probe into their medial temporal lobe to try and locate the epicenter of whatever epileptic events they were having. And typically, when this is done, the probe is put in and just some random stimuli are shown to the patient. So this group said, hey, can you show your patients some stimuli that we would think that could test some interesting properties of medial temporal lobe? And so what they found, maybe you all have heard of this, what they found is that units that they were measuring from had very, very idiosyncratic response properties. So for instance, one unit responded only, or was most responsive, I should say, to pictures of Jennifer Aniston, regardless of pose, background, hairstyle. Another unit was responsive to, what's her name, Halle Berry. It's a little dated now. Halle Berry. And if you notice there, it's not just real pictures of Halle Berry, it's also sketches. It's also the name Halle Berry. So there's some semantic level information at these higher level areas of information processing in the medial temporal lobe that are lacking from models like HMax. Similarly, the Sydney Opera House, there was a unit that responded to this from all different angles, as well as the word Sydney Opera House. Did I say that? Yeah, Sydney Opera, there we go. So that's one limitation, is HMax is not expressive enough. Another limitation is that it doesn't really do a good job of explaining what happens between V1 and IT. So there's V2 and V4, And really, these regions, in case any of you are interested in neuroscience, are an open question as to their response properties. So some have shown that they respond to these kind of curvilinear, closed shapes. Others have shown that they respond to kind of pinwheel patterns and gratings, like I showed you earlier, all the way up to other kinds of complex geometric shapes. And still others have found strong clustering or sensitivity to different texture statistics, so different textures that have been presented to animals. Another limitation is HMax, and these unsupervised models don't work as well as supervised ones. So of course, we all know about deep neural networks. And as I mentioned, the distinction here is that HMax was developed without backprop, with the goal in mind to explain neural data, and CNNs weren't. But that's not a bad thing, because recent work by Dan Gaymans and Jim DiCarlo and others have shown that you can derive better explanations for neural activity from CNN. So in this study, they recorded from primate V4 in IT, so these higher processing regions of visual cortex. And they recorded from those regions as they showed primates images of objects against rendered backgrounds. Let me just push through this. And what they found is that when they took a CNN and they optimized it for object classification performance, so that's on the x-axis here, they found emergent abilities to do a good job at explaining IT activity elicited by each of these scenes. So that's on the y-axis there. In this HMO model, which is just a hyperparameter optimized version of the CNN, of a specific kind of CNN, ended up explaining approximately 50% of the explainable variance in IT simply by optimizing for object classification. So this is really cool, right? Because they have dropped any constraints of trying to use biophysically realistic receptive field sizes or normalizations like the HMax did, and just said, hey, let's learn filters that explain visual cortex activity. So CNNs are great. That's why we're all here. But let me make a pitch for why they are not yet good enough. And part of this pitch is basically just borrowing from John's slides, which is that they lack the whole array of complex computations also available to biological vision. And this goes above and beyond simple feed-forward operations implemented by CNN. So there's a far greater proportion of feedback connections in cortex than there are feed-forward connections. And those must be there for a good reason, hopefully. One of those reasons can be to allow us to attend to different parts of an image to potentially increase efficiency of processing. And another reason could be to help us in tasks that require visual reasoning. So this is a little task for the audience. I know it's late, but please bear with me. So I'm showing you two classes of stimuli. Two images on the left belong to one class. Two images on the right belong to another class. What is the rule that separates these classes? Yell it out. What is that? Same, different. Yeah, that's exactly right. So are the objects in the canvas on the left the same? Yes. Are the objects in the canvas on the right the same? No. It turns out that this is a very difficult task for feed-forward models to learn, which makes a ton of sense because just intuitively right now, how are you solving that task? You're saccading between the different objects, and probably you're remembering something about those objects and comparing that mental image. These are mechanisms that are absent from nearly all convolutional neural networks. Another similar task would be to evaluate the enclosure of objects. So are the two objects are the two images on the left depicting enclosed objects? Yes. Are the two on the right? No. This is potentially dated for some in the audience in terms of the people that it's showing. Does anybody have any idea who's on the left? Ronald Reagan, yeah. Let's go through. Who's next?
George Costanza.
That's right. That's interesting, yeah. I don't think he would appreciate that. But, and next to him? Okay, next. Okay. Robin Williams, yeah. And finally? Okay, that's great. And well, maybe if you were here for the introduction, you saw these images. But I'll just assume that you have never seen these images before, and yet you were able to generalize your knowledge of these people to these transformed versions. Similarly with the blurred version. Is that Saddam Hussein, I think? Yeah. Another example of this power of visual reasoning in biological vision systems is from Josh Tenenbaum, 2005 paper where he tested one-shot learning. So given the plant on the left, which of the plants on the right belong to the same order? Well, you can see it's the two. Actually, it's more than that. It's several of those plants on the right, and it's probably not very hard to pick those out. One other aspect that's missing from CNNs these days is the ability to naturally segment objects from the surroundings. So the notion of object as an atom for processing is absent from CNN. Even per pixel prediction, CNNs rather evaluate every pixel in terms of a objectness. And cognitive psychology, cognitive science has worked for years to understand how the symbolic understanding of objects helps us reason about the world that we live in. And finally, a pitch, which is that potentially one way of bridging this gap, very naturally, given the learning systems that we use, is to use more biologically realistic training data sets. So what I'm showing you here are videos from a project in our lab called the Smart Playroom, where we place a camera on the head of toddlers and just observe as they interact with objects. And you can see right here the way that the toddlers are looking at the objects, morphing the objects. Maybe this is biological data augmentation, I don't know. But it's surely different than the classic, I missed it, but the classic LeNet, you guys have all seen that, LeNet MNIST training. So just to finish up, I've told you about this basic unit of feed-forward processing, this linear, nonlinear model, which consists of simple cells, normalizations, and complex cells. I've extended that to hierarchical processing, so repeating this computational unit in a stack was the principle behind many models for visual cortex, including the HMax, and has in parallel, let's just say in parallel, become a part of computer vision models. And finally, I hope I've convinced you that some of the inductive biases that are implemented by the visual system are missing from computer vision. And it's a worthwhile test to figure out which of these are important and which of these can help computer vision. So anyway, thank you all. Any questions? Yeah.
One question regarding cooling. So the way that is being done currently in CNNs, right? So you look at each feature map after convolution, let's say 3x3 neighborhood, and just take the maximum or average or something from that, right? But still you're looking at the response from one field. Now, if you look at these examples that you showed, right? So you show, or what John showed, right? So you show a bar at certain orientation, and then you add another bar in another different orientation. This becomes different from this CNN, right? Because now you're looking at the responses for two different things at the same field, right?
Yeah. Well, so the idea going back to the.
Whereas in CNN, basically you're looking at the space.
Yeah.
You're putting this at word space.
Right.
What you're looking at the same location, but at different features. It's one of the different features and speak of which one.
Yeah, so I think computationally they're the same. The idea that I presented here is that you have cells responsive to things that maybe are in the same receptive field, and those will project, basically their filters will be combined at a higher stage. So you can.
But I'm saying it's different than CNN, right?
But what I think is computationally similar, if not the same, is that you subsample with CNNs, you subsample the activity maps, and then learn a filter on top of that. So you're learning an AND operation on top of the OR, which I think would provide the same kind of sensitivity that you're talking about.
Well, again, the pooling, right? So with pooling, you don't mix different maps, different responses.
But that's what I'm saying. You need the additional convolution. Yes.
Yeah, well, that's a different story, right? Because that's
The abstractions from biological vision that are important for computer vision are very loose, right? So I think people have tried doing the pooling of filters that you're talking about, and I just don't think it trains as well. I think I've tried this in my PhD. I don't think it trains as well. And so when you have the ability to have larger gradients, basically, or more gradients to train your model, which is what this pooling followed by linear convolution followed by pooling can do for you, I think that it's simply an implementational difference. So computation, if we're talking about Mars framework, right? Computationally, I believe they're doing the same thing. Maybe somebody has another idea. Implementation, it's different. I'm of the opinion that we should take a computational inspiration from visual system. Implementation is interesting, may be useful, but not necessary.
I think my confusion comes from, if you can go to one of your slides when you had this cartoonic, basically pictures for and pooling. This one.
This guy, yeah.
Right. So on the right, basically you show wherever is in the receptive field, you still get the response, different scales and stuff, right?
Yeah.
But this is different than if you go to the next slides. The one that was basically putting two orientations and showing it was the one that also you had to put before display this checker.
The pool, it's gonna be tough for me to find. Yeah. So what's the question?
Yeah.
Yes.
So on the left, basically you have two different orientations shown in the same receptivity, right? Not the
I
same
believe so.
orientation,
Yeah.
different location. Basically, what I'm saying is that diagram doesn't tell that this is pooling. This just says anywhere in the receptive field you get a response. But if you want to say it's max pooling, you add something that the cell is not.
Yeah, I get what you're understanding. I'll have to review that paper. Yeah. Okay. Yes.
You mentioned about some missing inductive biases that you can learn from biology.
Yeah.
What might be some concrete examples towards those that you think basically
Right.
is only looking from?
Yeah, so one, which I did not mention today, is horizontal connection. So there's a large body of work by Stephen Grossberg and Charles Gilbert. So Stephen Grossberg's the more computational neuroscience. Charles Gilbert's the neuroscience, where they discuss horizontal connections. So this is between neurons in a population, can be the substrate for perceptually interesting phenomena like Gestalt rules, perceptual grouping. And so the reason why that's important, and I didn't get into this at all, is that this feed-forward architecture, it's repeating a template learning strategy. And when you repeat a template learning strategy, that can expose you to very poor sample complexity. Versus if you can learn a rule that can be applied locally, you can get around some of those issues. That's one way of doing it. Another reason for that is if you have horizontal connections and you pair that with recurrence, you can grow the influence of one neuron and its neighbors. I believe John showed some center-surround interactions. It's somewhat similar to that, in which you have a receptive field that's influenced by receptive fields around it. And if you have recurrence and horizontal connections, that means you don't need the many additional layers. You don't need 151 layers of a ResNet to potentially solve a pretty simple problem, simply because that is the number of layers necessary to grow a receptive field large enough to solve the problem, if that makes sense. So you can tag nearby receptive fields that are relevant to a task. You can take their computational resources to solve that task much more efficiently. Yeah. Cool. Yeah.
So there's been papers that have shown that like these feed-forward neural networks, the convolutional neural networks, can be fooled very easily by like adding some noise to images,
Yeah.
or by creating like noisy images that look like something suddenly. And so, do you think that's all because there's no top-down, or do you think again there's something wrong in the model itself?
Yeah.
Because you can fit it to fit neural activity, but then you can show that it actually acts very, very differently than neural activity.
That's true. Yeah.
And so I don't know if you have any.
How do you reconcile the presence of, so you're talking about adversarial noise?
There's like
or,
things where like you add a tiny bit of noise.
Yeah.
Like humans won't even notice the noise.
Yeah, so I would characterize that as a pathology of discriminative models, discriminative classifiers in general. So there's a lot of perspectives on the visual system that it through this dynamic experience that we have, essentially you're making moment-to-moment predictions about what happens next. It's a more generative style model. So potentially that kind of fundamental difference could afford visual systems a little bit more, or maybe complete protection from adversarial style noise. There's other recent work from Matthias Becke's group and Frank Tong's group where they show that simply adding Gaussian noise of different sigmas, training a network on that will give the network no ability to generalize to images from ImageNet with Gaussians of sigmas that were not in the training set. So this is a bit more like, this is a bit different, I think, in terms of the problem that's going on with CNNs there, which would be more of just the tolerances that are built up through this linear, nonlinear building block is insufficient, or it doesn't do a good job, I guess, of capturing robust vision of biological systems. I don't have much of an answer other than the hand-wavy, top-down feedback helps, but I don't know how it helps, other than to say that, Shimon Ullman has done a lot of great work on this. Rolf Semme has also done a ton of great work on this, on how these, moving beyond feed-forward vision, the kinds of operations that can help build up more robust vision. Cool. Okay, thank you all.
Okay, so last but not least today, the end of all of the visual processing we've been talking about is to get up to object recognition. I'm Mazyar Fallah. I'm at York University in Center for Vision Research, and I've been spending my career studying what I wouldn't necessarily call human vision directly, but often through animal models. So I'm going to use this talk as a way of answering questions, problems and questions when it comes to visual processing and objects. And the first question, of course, is what is object recognition? There are many different objects in the world. These objects, there we go. So we can see the Apple logo, a TARDIS, a Miata, a hammer, and MC Hammer. They all look very different. You can identify them as all being different from each other. The idea behind object recognition is to understand what each object is, what they do, or what you can do with them. And that leads to various questions like, which ones of these can you eat? Which ones of these can you ride in? And which ones of these can wrap? There's a lot of semantic information and background information that you're associating with an object when you recognize it. When you're given an object you've never seen before, you really don't know what to do with it. You start trying to relate it to other objects you know to decide, should I eat it or shouldn't I eat it? So in this sense, object recognition at the end of the day is to provide you with a reference ID. And it's a reference ID for knowledge, so the knowledge could be representational. This looks like there is a hot liquid in a glass. It's probably a cup of coffee. Semantic information. So in this case, here's the radiation symbol. You see the symbol, you know that there's radiation nearby. You haven't seen radiation, but the symbol represents that the radiation is there and you should take care. It also deals with actions and affordances. Here's a hammer. The affordance means I should be holding it by the handle and not by the claw. It's about decision making. When you have a hammer, everything looks like a nail. And it's about outcomes. When you've done something good and somebody smiles and gives you a thumbs up, you can recognize this expression and action to mean something, in this case, well done. So where are objects represented along the visual system? Well, mostly, as we've been talking about in the earlier talks, we're going to deal with shape being selective along the ventral stream over here, ending up in inferotemporal cortex. But I'm also going to draw your attention to STP over here for some of my very last slides, where we'll also find some object representations. So the first problem with objects is to determine whose border is that. What we have here is the Rubin's vase illusion, and as Krista talked about, there's a figure ground segmentation problem that goes along with it. So when you see the vase, the border is owned by the vase. When you see the face, the border is owned by the face. The idea is that a contrast border can only be owned by a single object at a time, and whatever doesn't own it likely falls behind it, and therefore is the ground. And that means that the visual system has to recognize when this contour is part of this object on the left or part of this object on the right. The contour is the same. The cells that represent that contour in the earlier levels will see the same thing, but they will be able to differentially represent which object it's associated with. We find that type of effect as early as V2 in the visual system. So here's a V2 neuron just south of fixation. And it likes a contrast border with light on the left and dark on the right. And it gives a nice big response. None of this is working. Nice big response down there on the very left-hand side, about 15 spikes a second. But when we look down here at B, we have the same identical image in the receptive field. It sees the same photons of light on the left, dark on the right, in an oriented bar. But the response now is dropped out. So this is not a contrast contour or border detector, liking light on one side and dark on the other. What it actually represents is the side the object is on. Which object owns that border? And so this cell is a cell that represents the border is owned by the object on the left. It doesn't matter what the contrast is. You can flip contrast polarity, go dark on the left and light on the right, and you get the same response. It likes the object on the left more than on the right. And similarly, as you increase the size of the object, you change the size. Again, you have selectivity for the object on the left. Now, it is using Gestalt rules about the figure being smaller than the background or having these edges here delineating which one's the object and which is the background to tell which side the border should be associated with for figure ground segmentation, but the cells in V2 are starting to represent an object. This object is on the left. This happens quite quickly. In V2, you get an object selective response in 68 milliseconds, in V4 in 73 milliseconds, extremely quickly. There's a related problem that goes along with whose border is that, and that goes, where's my border? We live in a world where a lot of things can be occluded by other objects. I'm standing up here and talking to you, but nobody thinks I'm a head without legs. You know my legs are behind this. And similarly, sometimes you might have an object on top of another object that is camouflaged. So we've got a rectangle here, and again, we've got a V2 cell that likes an oriented contrast border. And as that rectangle moves up and to the left, we get a nice neural response. But if we now put that same rectangular bar on top of black and white striped background, this same receptive field will never change. It sees the same weight the entire time through as that bar moves. But again, we get a slightly less response, but there's still a response. It is representing the border that is there. It sees a border that does not exist by photons. So we have a response that is finding the border of an object even if that border is not visible to you. The same thing would happen with occlusion. If that border was underneath something, you would still find V2 cells that would represent the occluded border. This is thought to be done by a collinearity rule from Gestalt rules, suggesting that there's a unit up here and a unit down here that both feed into the central unit with an AND function. So as long as both of these get a response at the same time, this cell fires. It's backed up by the fact that if you remove one of the two sides, so one of the two side units is not present, you don't get a response. The other side unit not present, you don't get a response. So this could be potentially done in a feed-forward or a same-level manner. Is that one working? There we go. Okay. Now, you've seen earlier, shape selectivity is important in the ventral stream, and shape selectivity increases in complexity as you go along the ventral stream, getting up to the most complex objects in anterior IT. I'm not going to go into how that is worked out because it was quite well taken care of. But I will go into how it's organized, because that's important when it comes to object recognition. We start off in IT Cortex with these columns. And a column represents an object. So in this case, it's a tri-armed object where each arm is equi-angled apart from each other. And so we've got a series of cells going all the way through that represent this type of object, and that forms a column. But the next organization is actually in the sense of a hypercolumn. And what this hypercolumn has is similar objects that vary along a dimension. So all of these are tri-armed objects, but the angles between the arms change as you move along this dimensional axis. And so this takes individual objects, creating these dimensional complex feature representations for parts of objects. And you can see the same thing happens for the monkey face as it rotates, or this little depth Q as that rotates around, or the number of arms coming out of a star shape, or an oval or a circle that's being rotated in space. So we represent parts of objects in a dimensional axis type form within IT Cortex. From these parts, we can then put them together in a dynamic network attachment system across the different parts of these columns or hypercolumns to create objects. And this was shown with the idea of geons. And so here's a geon for a curved tube. Here's a geon for a cylinder. If we put them together in one orientation spatially, we can get a cup. If we put it in another orientation, we get a pail. We can take the same handle type geon, add a polyhedron, and we can make a suitcase. So a complex object is made up of recognizing smaller parts of objects and then looking for the pattern of responses with a spatial representation between them to define the individual objects. Does that happen in IT Cortex? That's a great concept. But it actually does work that way. So in this study, what they did was use batons. And a baton is a vertical bar that has a top end and a bottom end to it. And they created sets that were 2 by 2. So the top baton is the same across a row, but changes as you switch rows. The bottom baton is the same within a column, but changes as you switch columns in the 2 by 2. And here's a neuron that just responds to any type of baton. It can't tell you what the part of the baton is. It's not selective for the whole baton. So it's actually fairly useless as a neuron. And there are a number of these fairly useless neurons in the brain. But now we can move up to a neuron that's like that column we saw earlier. It likes a specific part. So this neuron here responds well when there's an oval at the top of a baton. It doesn't care what's at the bottom of a baton. If there's no oval at the top, no response. But whether you've got a cross or you've got this thing, the spade, it just doesn't matter. So it's responding to the part. Now, if you take 2 part neurons, they can feed into a third neuron that is now showing the effects of liking 2 different parts, getting input from 2 parts. So what we have here is a neuron that responds to a trident on the top and a hexagon at the bottom. When either of those are alone, you get a nice response. When they show up together, you get a multiplicative response. The response is higher, representing that both parts are there. And so this neuron isn't necessarily selective for this shape, but it's selective for a combination of these 3 because it can feed in individually from one part of the object, but it also gives you a multiplicative, stronger response when both parts are present. And finally, we have an actual object-selective neuron here, where in this case, it only likes a star on the top and an arrow on the bottom. Stars on the top alone, arrows on the bottom alone don't really give you any response. So this is again working like an AND type system, so that when you have an arrow at the bottom and a star at the top, if you have part neurons that represent the arrow and the star, and they both feed into this neuron with an AND function, when they're both active, this neuron fires as a result of it. And that makes it selective for the combination of parts. Now you can take this idea with the geons and extend it out to represent any type of complex hierarchical object in the visual world. So that takes us to our next problem. It's a problem about beer. We're getting late in the day. On the last talk before the cocktail party, you want to go out and get a beer as soon as this is over. So you order a beer up at the bar, and it's up at the bar and it's waiting for you. So you see the beer over there and you say, this is my beer. And now you walk up to the bar to get it. When you get up to the bar, the image on your retina is much larger because you're a lot closer to the beer. You don't think your beer has changed. That bartender didn't see you walk over there and decide to put down the 62-ounce mug instead. You know it's the same object. Object recognition requires stability across changes in size in the retinal image. And that's size invariance. Similarly, position is also important. That's up at the bar. You want to go get it, but this time it's very crowded. So you have to walk around people, and you're turning and moving around them. And as you do so, the image of your beer on the bar moves to different parts of your retina as you move and your eyes move around the world. And as they move around, you don't all of a sudden think, hey, now I've got 3 beers. It was in 3 different retinal positions, but you know it's still the same object. So you need stability for a change in position on the retina to continue to represent the same object. Similarly, if the bartender put it down in one place, and as he saw you coming over, moved it down the bar towards you, you wouldn't think it's a different beer because it's changed positions in space. It is still the same beer. We need invariance of position. And finally, it's viewpoint. You're walking up, you grab your beer, finally it's nice and big, you take a sip, you put it down, you spin it around, and now the handle's facing the other way, and you don't think it's a different beer because the handle's on the other side. Objects need to be stable as your viewpoint around them changes because objects often are asymmetrical in nature, 3D shape at least. So does IT neurons do this? Sure, and it's not just about familiar objects. So in this study, they used wireframes of different shapes and then combined and tested neurons till they found out what shape it liked. And they were all done with this basic size here. And they found the wireframe that the neuron was selective for. And then they knocked it down to 40% size or increased it to 250% of its original size. And what you can see here from the response is stable across a wide range of sizes, from 40% of original up to 250%, or a 6-fold change in size. No difference in response. So this is a size invariant neuron. The image on the retina, the size of it should not matter for recognizing the object, and this neuron does just that in IT cortex. Same thing for position invariance. In this case, the black background is the response when the image is at the center of fixation from that last slide I showed you. And there is a slight advantage. Neuronal firing rates are higher when objects are centered at the point you're looking at. It's often considered to be part of potentially automatic overt attention. But what we have here then is moving that same wireframe all around the image, everywhere else within the receptive field. And this gray response in front is pretty stable across those position changes. So it's still representing the object regardless of where it is in your visual field. You need that to recognize objects. Viewpoint invariance, here's a hand cell. Your hand can be in all sorts of different orientations and moving in different directions, and you get a pretty stable response. It doesn't matter which way the hand is facing, it represents a hand being there. Now, viewpoint invariance is good for recognizing objects, but there are some tasks that you want to do where you recognize an object, but you need a specific viewpoint. So here's an example again from Charlie Gross's lab, where we've got a monkey face recording from monkey cells, and this neuron likes a monkey face with a frontal view. We get good responses when you can see the front. When it turns to the side or goes around behind, the response is low, and here's the firing rate over the head rotation angles. And this is the image without any eyes. So you can see generally it represents up to about here, but once you get to 80 degrees or further, there's really no good response for it. Why would you need to do this? Well, because what else do we recognize off of a face? Not just that it's a monkey face or the identity of it, but the facial expression, the emotions. If the monkey's just looking at you passively like that, no big deal. If the monkey is burying 5-inch fangs, you probably want to step back. So you need to have specific viewpoints to do specific types of recognition, and we have cells that can do that as well. Now here's another one going back to the wireframes. The monkey one's a very easy example, but it's a wide range. That was up to 80 degrees of rotation. So here's wireframes, again, that aren't natural objects you normally see in the environment, but this cell likes mirror-symmetric wireframes, 180 degrees apart. It's selected for these two specific images. Why mirror symmetry? Well, we evolved in a world where most things are bilaterally symmetrical, especially along the vertical axis. And then we build our man-made objects the same way, so there's bilateral symmetry. And a lot of times you will walk around different sides of the object, the front or the back, and you want to be able to recognize it regardless of which symmetric viewpoint you're getting from that object. And so there may be this holdover that we evolved in a bilateral symmetry world that gives us cells that are specifically bilaterally symmetric. If for some reason everything was trilaterally symmetric, we all had 3 legs and 3 arms and built like tripods, then maybe we'd have trilaterally symmetric neurons instead. That brings us to our next problem, and the good one. How do we distinguish individual objects of the same type? So up till now, we've seen shape selectivity is important. We've seen what we need to keep invariant so we can respond to a selective shape. But now that we get the shape, there's a lot of different objects that match that shape. There are a lot of different chairs in the world. There are a lot of different dogs in the world. There are a lot of different Cocker Spaniels in the world. You can still distinguish between them. You can identify an individual item. The place where this is the most studied in the brain comes from face processing. We recognize individuals based on faces. We need to process faces for social cues. So we've studied how face processing works extensively. Faces are complex objects. They're made up of multiple features, but everyone's got 2 eyes, a nose, a mouth, 2 ears. Well, most of us do. And because of that, they all have generally the same features, but yet we can identify very different individuals having the same features. So if we can understand how face processing gets us to an identity, then we can understand how the visual system recognizes individual objects of any type of category. So Charlie Gross actually found face cells first. In fact, he found hand cells first. Recording from IT cortex, I showed you some of those complexity maps of the different types of parts of objects. They were using all sorts of weird shapes and geons to get around it. Found a patch of cells where they just couldn't find any geons causing any responses. And they kept going back and recording there day after day after day until Charlie got very frustrated and at one point said something on the equivalent of, "Oh, screw that," and just waved his hand in front of the screen, and the cell went crazy. So then they started testing that area and found that it was responsive to body parts. Some cells liked hands, but the majority of cells responded to faces. And this led to a large number of studies around face cells in IT cortex, because here are very specific objects that we need to understand how they work. So here is a very parametric study, well, parametric for 1994. You see there's no stats up here. Looking at what makes a face cell. You show it a monkey face, it gets a response. But in fact, a caricature gets a much stronger response. So it's looking for 2 dark eyes, a dark horizontal mouth, in a circle with a slight contrast difference of the skin versus the background. Okay, so based on what we did with the batons, are there part cells feeding into this? Is this a multiplicative effect? Or is it representing the face holistically? If you take out the mouth, no response. So the first question is, maybe this is a cell that responds to mouths. So you give it the mouth alone, no response. Okay, doesn't respond to mouths. If I add these 2 up, I get that image. Can't do that here. So what if it's just the 2 eyes and the mouth in relation to each other? No response. Now, I will say this is in a square instead of a circle. It's 1994. Nobody was showing monkeys SpongeBob SquarePants. Nowadays, if you show them lots of cartoon videos and you show them a lot of SpongeBob SquarePants, they might actually treat that as a face. But back then, they didn't. Faces were round or oval, so it didn't fit. What if you just show the oval? Nothing. You could put the circle within the square, and you still got the outline of a face, and you go back to the original response. So you didn't need this contrast border. You needed the circular contour with two dark pits and a dark mouth. Flip the contrast contrast polarities, no response. We don't have glowing eyes and glowing mouths. That's not a face. So it's a holistic representation of a series of parts with a specific spatial relationship that causes this cell to fire, and not any of the subparts. That led to the idea of, well, then how do you identify individuals? And the first idea that came up there was the idea of a grandmother cell. And that is, maybe you have a cell in your brain that recognizes each person you've ever met in your life. So you'll have one cell in your brain that represents your grandmother. And it's a nice idea, except for a couple of problems in actual implementation in the world. And one of the problems is, do you have enough face cells to represent every single different person you met? I mean, at some point you'd run out of face cells and everybody else would look the same as not face. The second problem is, I've just killed 100 cells by jumping up and down. What if I lost my grandmother's cell by doing that and I can never recognize my grandmother again? It's not a good redundant system for the world we live in. So that led to the idea of population coding, where you use a variety of neurons taken together to identify an individual. So that goes against this slide that we saw before, where you will find a cell that specifically responds to Jennifer Aniston, regardless of the image you give of her across time, size, direction. But also what's funny is that it doesn't respond to Jennifer Aniston when Brad Pitt's in the image. Right? So we're not getting any biased competition here. As soon as Brad's there, not interested in Jennifer at all. Take that as you will. You can always find cells that are highly selective and appear to be like a grandmother cell. But the question is, what do the majority of cells do? How do we really use an encoding process like this? And that leads to the idea of face space. And this is the culmination of decades of research. So don't take it as Leopold is the first and only person to ever come up with this idea, but it's built upon a long line of research. And the idea here is that if you give people, or monkeys, 4 individual faces that they're going to have to discriminate between. Here are 4 faces. You got a 4-button controller. When you see face 1, press left, face 2, press right, face 3, press up, face 4, press down, etc. And I'm just going to show you a bunch of images, and you have to distinguish between them. Okay, great. Well, what actually happens in the background is you take the 4 faces and you average them into a prototype. And the prototype is the average of all 4 faces. And then you have a vector in each dimension for one of the given faces that goes into this average. Now, what individuals are doing is then comparing the image they see with their prototype in face space and determining what vector direction does that image look like it's part of. And this is based on features of the face. So for example, the distance between the 2 eyes, the distance between the eyes and the tip of the nose, the width of the cheeks compared to the height of the chin to the top of the head. So if you take various dimensions across the face, and note, I'm giving you features that are not deformable. Most of the time, we can't change how far apart our eyes are. You don't want to use features in face space that can change very easily. And that's what determines these dimensions in face space to get it. And so you do this, and people are very good at these 4 faces, but the interesting thing is that you can then take a face that is a weighted average and not an equal average, so it falls along one of these dimensions. So these faces here, and the individuals, the monkeys or people, have never seen those images before, those averagings. When you give it to them, they're still very good at identifying them. They can tell you which face it's predominantly made up of. They can tell you what axis it's along. So this leads to the idea that we have a multidimensional face space, and we have selective identification of faces based upon a figural comparison. You compare your incoming image with your prototype, your internal template from the center of this face space. IT neurons that they then recorded from do exactly that. So here's an IT neuron that is selective for face 2. And so a light color is a high response and a dark color is a low response. It's selective for face 2 and really doesn't like face 1. Here's another one that's really selective for face 3. And so you get a variety of these patterns for face space along these axes. So we're starting to see that faces are coded by this multidimensional space. Now, we have only tested them on these axes that we've given them training information for individual faces on. If it's really face space, you should be able to take a face made up of any average in this 3D sphere, test it, and have neurons respond selectively to it. Have the individuals be able to categorize it. And that's what we see here. So we've got a number of points that aren't on the axes for the 4 spaces we've used, and so they're giving us a combination of these non-deformable features that are different than what you see. If this guy over here has close beady eyes, but a long oval head, and this guy over here has a long oval head, but far apart eyes, then an individual in here has a different combination, has an average of the eye distance with the same oval distance up and down. That would look different than either of the other two, right? And so you test within these, and this neuron here actually likes somebody that's a mixture of face 2 and face 3. So the preferred vector of selectivity in face space for this neuron is this direction. And each of these other ones has a preferred vector in face space for what they are most selective for. So this leads to population coding for face space. Really is based on each neuron having a selectivity vector in multidimensional space. You can combine these vectors across the population, and it'll produce a peak response for any given image that is representing the identity of that face. And the fact that we're using this population allows for small changes to not appreciably affect the population peak response. So when somebody puts on glasses or is wearing contacts, you'll have small changes in the image that might be harder, well, it used to be much harder for computer vision to handle things like facial hair, haircuts, and glasses or not. But the human face space vision, because it's based on the non-deformable factors, and because it's looking for the peak, one of these changes will reduce the response to all of the neurons, but the peak will stay in the same place. So it's robust to small facial image changes. Now, this type of population coding can be generalized to all types of objects, and this is also what's going to give rise to categorization, as mentioned earlier. So you can categorize things as a car versus a dog very quickly. Within the car category, you have subcategories, and you can categorize a sedan versus a pickup truck very quickly, if that's your task at hand. So that works in the same way. Population coding that's working in the rest of the IT cortex for the type of objects that are there follows the same principles. So you have a neuronal population from 1 to n. You can give it a whole variety of images, and you look at the pattern of responses for each neuron. If you plot the response for each neuron on its own axis in n-dimensional space for the n neurons, you can end up with a single point in an n-dimensional vector that is giving you the representation for a specific image. When you plot all of these out, you get these clouds based on categories. Then you can find a hyperplane that maximizes the distance between the plane and every point of a given category. So in this case, this is a hyperplane to determine what is a car category from everything else, not car. And it's working on the same concept we saw in face space. Using a neuronal population in a multidimensional space, the vectors give you individual points. You can do that across more than a single category. We've got 4 different types of images here representing different objects. Again, we've got a series of neurons, and they're going to produce a vector in multidimensional space for a given image. You give it a different image, you get different vectors, and these vectors tend to cluster across multiple representations or multiple presentations of the same image because there's noise in the system. But similarly, if you had modifications of the monkey faces in C, they would all tend to cluster in the same area as well. It would just be quite a little bit broader. And so what we're seeing here is that the organization at the end of the day isn't necessarily about the parts being next to each other in columns. It's not about the hypercolumns made along a dimension of those parts, but it's about the pattern across columns and hypercolumns for parts of objects representing whole objects. Those pattern responses are going to produce these multidimensional vectors when you record over a wide variety of neurons. That gives you an individual identity, or in a rough zone with a hyperplane can give you categorization. And then, of course, you can train a linear classifier to determine what's in category A, and then test it with additional trials you hadn't recorded from before to see what your performance is like, but I'm not going to get into that. What I do want to do is move along to the difference between categorization and identification. Categorization is very quick. You can tell what category something is in if you know that you're trying to choose cars versus not cars, or you want to categorize animals as quickly as you see them, or you're looking for fruit. Category comes very quickly, and in fact, it doesn't take very many sites or neurons if you spread them across IT cortex to be able to categorize something. If you put 64 sites all in the same small hypercolumn, it's going to be very hard to categorize a lot of different objects. But if you spread them out, 64 sites across that map will give you pretty good categorization performance. What's next important is how you get to identification. So in the face space examples, we were looking within the cluster in a zone to get you that information. And then you do that comparison to prototype like we saw with face space. That is the best way to identify somebody. But in fact, computationally, you can use the same broad range of neurons across categories to identify somebody, but it takes a lot more sites. So what I'm saying here is one face, for whatever reason, might slightly resemble a pair. So you're going to get a slight response on your pair neurons for one face versus a different face. And you might get a slightly different response around cars because you just saw cars, you like Lightning McQueen, and you think the guy's eyes look like Lightning McQueen's. If you look at a wide range of responses, you can find that you can identify individual images in your test set. Now, what we haven't done, I haven't done any of this computational modeling, what people haven't done is try to generalize it to every possible image out there. But the basic concept is still there. So what we have is, in their imaging studies, they look for activity in clusters. And so they find the hypercluster for face cells, and they call it a face area. They find another zone of the brain at the other end of IT cortex that is representative of places, houses, buildings. So constructs that are rectangular in nature that you go inside, and they have a lot of other squares or rectangles on them, windows and doors. Those are very far apart. Faces have very few right angles and don't have multiple right angles. Houses do. They're at different ends of the spectrum, but they're not really separate areas. There's a gradient of responses from round to rectangular, and they cross. And as long as you get enough sites across it, you can identify. But identification takes a lot more sites and takes more time. So this leads to one last point that I want to make on this topic, which is what actually defines a category. So far, I've been giving you very distinct categories because distinct categories are easy to test. Dog versus car. Easy to test that. You'll get the best difference in your responses in the brain when you do that. And so here's an object that has nothing really to do with the ventral stream. Person doing a backflip. We saw biological motion before walking. We can see all sorts of actions that happen. There's an area in the brain, STP. From that first slide, I said we're going to talk about STP. This is STP. It gets input from the dorsal stream, from motion processing, but it combines that motion processing into templates for what a human body looks like. And then it can combine those motions to form an object. That object representation that's coming out of there will still feed into IT cortex so for you to identify it as a person. So we can get objects also just out of motion. But we can go further. Here's a category of people, of people's motion, and that is gender. You can get gender from the gait. Left-hand side, woman. Right-hand side, man. Female and male. The center one is a 50-50 equal morph of the two, an equal average. So what's interesting, is if you want to play with your after images, you can fixate on the woman while the movie's playing, and then after a second or two, flip your eyes over to the man, and the man will look more masculine. And vice versa. So we actually studied that and showed how that works in the sense that when you adapt to a single gender that's only defined by how the dots move, you can actually take an ambiguous figure and shift it to appear of the opposite gender. We have gender space for biological motion. So then that leads to the real task for object recognition. What we have up to now is a representation for an individual object. But recognition involves memory processes. Once you represent a novel object, you want to start building up associations about it. If you've seen an object before, you want to access your knowledge about it. These go into the recognition process. So you meet a new person. I'm assuming nobody here has seen Joe before. He says, "Hi, I'm Joe." He's novel to you. Now you're going to want to start attaching his name to his face. So if you see him again, you remember his name. You don't want to be that guy who walks up to him and go, hey, he goes, "Hey, how you doing?" And you're like, good, right? I sort of recognize you. I don't remember who you are, right? So can you recognize Joe the next time you meet? We've gotten to the point where with face space, we have an identifier in multidimensional space that identifies Joe. So how do we use that identifier? Can we then determine what recognition is? Have I met him before? Is he familiar? Have I seen him recently? These are the types of memory functions that go along with object recognition. We have neurons that do this. So in perirhinal cortex, which is beyond IT cortex in the ventral stream, you end the ventral stream, you go to perirhinal, entorhinal, and then the hippocampus for your memory systems. Here's a neuron that's seen Joe for the first time. It's not actually Joe. That wasn't what they tested. What they basically did was showed a bunch of objects to these monkeys over a number of days till they had a familiar object set. And with any given day, they'd show them the objects a couple of times so you could see it for the first time that day or the second or third time that day. But it's a familiar object. And after a while of training, they started sneaking in new objects. When you see a new object for the very first time, this perirhinal neuron responds really well. But when you see it the second time that day, no response. You show it an object that's seen before, like a banana, for the first time that day, no response. Banana later, no response. So it codes novelty. Here's something I haven't seen before. That's useful for your memory system because maybe it keys into the memory system the same way attention works for visual processing. And so it primes the memory system to try to remember as much information as possible about this new object that you've never seen before. We have familiarity neurons. So this familiarity neuron actually is firing when it's not familiar. You've never seen this object before, it fires. But it's the second or third time you've seen it in the same day, but you really don't know what it is, it still fires. The familiar objects it doesn't give a response to. So again, now I've seen it, I'm seeing it again on the same day, but I'm not really familiar with it. I don't really know who Joe is. And finally, recency. So a recency neuron works on, whether it's familiar or novel, the first presentation of the day. Have I seen this recently? No. I know what it is, but I haven't seen it in a while. I haven't seen Joe in a while. I see him for the first time. I get a little spark of recognition. Joe! And that's what this neuron is doing here. But you see him again half an hour later, you're like, oh, that's just Joe. So the ventral stream object representation is an identifier that feeds into perirhinal and entorhinal cortex. We can do recency, familiarity, and novelty off of it, and it feeds into the hippocampal memory system. I'm not going to go into how memory works beyond the scope of this tutorial, and also probably beyond the scope of our time. But the last slide I want to give you here is about expertise. We're all experts with faces. That's why faces were easy to study, whether it's in a monkey or in a human. We all look at faces. But there's a lot of things that we might see repeatedly and build up expertise for. People who are bird watchers build up expertise for birds. People who are into classic cars build up expertise for classic cars. And they're just as good at those as you are at faces. So the question is, what happens with experience in your object recognition system? And so this group used and created a stimulus set called greebles. Greebles look like little faces of weird objects, weird things that don't exist in the real world. And they created a series of families and they created two genders. And so these were differences in dimensions of some of the things that are sticking out. So are they going up or down? Are they pointy or round? You know, what direction are different other things pointing in for the genders? And you can create a whole bunch of images in this line. So now what you're going to do is you're going to show somebody an image and ask them which family it belongs in and which gender it is. You put them in an MRI scanner, and I had to finally give in, and instead of showing you neuronal responses directly from recording, I had to go to an MRI for something here. And here's the face area that's active when you show them faces. You show it greebles, which have a lot of face-like features. And for a novice who's never seen greebles before, there's no response in the face area. Doesn't treat it as a face. Kind of looks like a face, but there's not enough activity for them to identify the face, and they do very poorly at the family and gender task. But you train them a lot till they do really well, and now they're an expert. You put them back in. You got your face areas, and now you get activity in the face areas when you show them greebles for greeble experts. So what's happened is there's plasticity of the representational space in IT cortex such that you use the average prototype and create more selective neurons along different vector angles away from it. That increases the size of the representational space for greebles that allows you to distinguish between the families and the genders. So you've increased the selectivity of tuning against the prototype as well as the amount of space you can do to distinguish between them. In fact, this has actually been found behaviorally when it comes to race and faces. If you take somebody who's a new immigrant to Canada from a country where they are of a different race to begin with, and they've primarily only seen faces that are a different race, they have a very small representational faces, or face space for Caucasian faces. And the reverse also is true. When you take somebody from a primarily Caucasian country who then travels to a country where it's non-Caucasian faces, they start off with a very small representational face space for that. You give them 2 weeks of walking around everyday life, seeing lots of faces without even trying, and then it's like that difference is completely gone. So it has fast plasticity that's very important as you travel around the world. Probably why we put it in there, right?
So do they lose the sensitivity to the ones that they already learned before?
So this has always been a very good question, and the best I can get at is that you seem to lose some sensitivity. The problem is we haven't really met the limits of it. How many things can you be truly expert at a given time that are overlapping within each other in IT cortex and in these representational spaces? There is likely a limit to it, and there's more work on that in the motor system with skill learning where they've tested it more often. And if you learn new skills, you do actually decrease or extinguish some of your abilities with other skills as you learn additional skills. But the amount of decrease drops with each additional new skill you learn. It's probably going to work the same way when it comes to object recognition. And then in summary, object recognition is based on a combination of features in n-dimensional space. The complexity increases across IT cortex. We get this population coding. We use it for categorization and identification in this n-dimensional space. And then we use that for recognition memory encoding. If you take anything home from me, I like to call it an ID. It identifies something that you can then attach memories to. And then within it, we also have plasticity based on experience. The more you have experience with things, you can adjust your representational space for those objects so that you become a better discriminator of it. Training trumps abilities. Everything will be on the reference list for what you've seen there. You feel free to check them all out. And it's going to be on the website for the slides along with a video for the talk. Happy to take questions.